theorem is a really important theorem in probability that talks about conditional probabilities. Let's see it in action in an actual example where we can analyze some real-world data and come up with a conclusion. Okay, suppose Arnold operates an order-filling machine that has an error rate of 0.6%. He installs a new order-filling machine that has an error rate of only 0.2%. The new machine takes over 85% of the order-filling tasks. Now, one day, Arnold gets a call from a customer complaining that his order wasn't filled properly. Arnold blames the problem on the old machine. Was he correct in doing so? Well, we're not going to be able to answer this question for absolute certainty because we can't go back in time and see which of the machines, the old one or the new one, actually filled the order. But we can use probability to say what we think is more likely than not. And to do so, we actually have to use the wonderful and important Bayes' theorem. Now, Bayes' theorem, let me just remind you, states that if you're given two events, A and B, and the probability that B occurs is not 0, then the probability that A occurs given that B has happened is equal to the probability that B occurs and A has happened times the probability of A, all divided by the probability of B. So, in some sense, if you want to find the probability that A occurs given B, if you know that what the probability of B occurring given A is, then you can actually use that to find this probability. Another way of writing this is to say the probability that A occurs given B is equal to the probability that B occurs given A times the probability of A divided by the sum of the probability that B occurs given A times the probability of A plus the probability that B occurs given that the complement or the opposite of A has occurred times the probability that the opposite of A occurs. Wow, a big mouthful, but it's a really important theorem, and we're going to see how it's going to be used right now. Let's check it out. So, the first thing we want to do is find the probability that the order was filled by the old machine given that there was an error. Because, in fact, Arnold thinks that it was the old machine, and we know there was an error. So we want to find the probability of old machine given that it was an error. So what I'm going to do is I'm actually going to make a little tree, a decision tree, sometimes it's called, where I'm going to take a look at the different scenarios for the machine. So there's two possibilities. We could either have the old machine or the new machine. And then in each case, there's a chance of an error or no error. In the new machine, there's a chance of an error or no error. And now what I'm going to do here on these little branches here are put down the probabilities that these things occur. Well, we know that the new machine is used 85% of the time, which automatically means that the old machine is in service for the remaining time, which is going to be 15% of the time. If I write those as probabilities or as decimals, then I could put in here 0.15 and 0.85, meaning that the probability that if I select a machine at random, given the probabilities that we have, the probability of going to the old machine is 0.15. The probability of having it to be the new machine is 0.85 because 85% of the time we're using the new machine. Okay, now what is the probability of seeing an error? Well, we were told the probability of seeing an error on the old machine was, let's see, it was 0.6%. And the probability of an error on the new machine was 0.2%. So if I change those percentages to decimals, then I see that the probability of error, if I have an old machine, the probability of error is going to be 0.006. The new machine, the probability of having an error is 0.002. I can now figure out the probability of no error in each case because the no error is the opposite of that. So it's 1 minus that. And the no error here is 1 minus that. So we take 1 minus that, it's a 0.99 something, in fact 0.994. And for this one, it's going to be 0.998. And so forth. So you get the idea. Now we filled this up. Now we want to figure out what's the probability of making it all the way down there. Well, if we talk through it, we can figure it out. So what's the probability that we start here with not knowing which machine? What's the probability of having the old machine and having an error? Well, the word "and" there is key, and these are independent events. So old machine, and then there's an error. So old machine and error, I multiply probabilities together. So I take 0.15 and I multiply it by 0.006, and I see the answer, which in this case is a very small number, 0.0009. And to get these other probabilities, I do the exact same thing. I take the probability of getting an old machine and the probability of no error. Then I multiply those two numbers together. For the new machine, I take the probability of getting the new machine and having an error, so I multiply these numbers together. Take the probability of having a new machine and no error, I multiply these numbers together. And if you do that, you see these probabilities right here. Okay, now we can put all this together. We made the tree diagram, and now we can actually use Bayes' theorem, because we see that, if I slide all this over a little bit, the probability of having an old machine, given that we have an error, which is what we're trying to figure out, is equal to the probability that we have an error given that the machine is old, and that we actually know. That probability we know is right here, times the probability of the old machine divided by the probability of an error. So let's put all the numbers in here. So for the first case, the first thing, we see the probability of having an error given that we're an old machine. Well, given that we are an old machine, the probability of an error is that, so we write that in there, multiplied by the probability of getting an old machine. Well, that's in fact right here. And we divide that by the probability of having an error at all. Well, having an error at all means that you have an error either on the old machine or on the new machine. And so it's either an error here or here. When I hear the word or, that means add in probability. So I take this number and add it to that number. And that's where we're using the tree diagram to get these numbers off. And if I add all those up and simplify, I see this crazy thing, which actually simplifies to a very nice fraction of 9/26, which is approximately 0.35. So, given that there's a mistake, the probability is about 35% that the old machine filled the order. Just 35%. Kind of surprising, isn't it, when you think about it, because, the old machine makes more mistakes than the new machine. The thing is that the new machine is only used 85% of the time, and the old machine is used only 15% of the time. So there's a really, really high chance that you're actually using the new machine, and it just made one of those very, very rare mistakes. So the chance that, in fact, it's the old machine, given that there's an error, is only 35%. And so the probability that the new machine fill the order is 65%. That's 1 minus 0.35. It's the opposite. And so therefore, just kind of from probability terms alone, just from the probability of it, we conclude that Arnold really shouldn't blame the old machine, because it's more likely than not, kind of from a probabilistic point of view, that in fact the new machine actually filled the order. And this is something that we see a lot when we look at interesting data like this, when there are two possibilities and there's a failure. These are also often called false positives. So a lot of times when people go in and get a medical checkup and they're told that they might actually have some kind of medical problem, well, they have to kind of do an extra test, because that test could be a false positive, because so many people do not have the disease. But from that great number of people that don't have the disease, a few of them will say, well, you know what? The test shows that you have the disease. Well, a small percentage of an enormous number is still a big number. So just because that test comes back positive, it could be a false positive, because so many people are healthy, and there's a tiny chance that you might actually, the test will come back and say that in fact you do have this disease, that in fact that number is actually quite large. That's exactly what's happening here. It's the same scenario, that even though it's more likely that the old machine will make an error, there's so many more filed orders with the new machine that a few of those are going to have an error, and there's going to be so many of them that they kind of dominate in a way. And so even though there's more errors happening on the old machine, since there are very few orders placed there, in fact, it's more likely it came from the new machine. A little bit counterintuitive, but really interesting, especially when you realize that sometimes even health issues involve this exact same principle. It's kind of good to know that sometimes if someone that we know gets a test result back that says that they might have a disease, that it really could be a false positive. That's exactly what we see here, and that was Arnold's mistake. Have fun looking at and uncovering the mistakes that we see around us, and I hope that probability and statistics will allow you to actually resolve those mistakes. I'll see you soon.